Okay. Hi, everyone. I'm Jason Mancuso. I'm the organizer of Caig, this meetup. And I just wanted to take a few minutes to talk about the group and introduce you if you haven't been here yet. This is only our second meeting. So I'm really glad you're here. Really glad about the amount of interest that we've had in this group so far. This is only our second meeting, and we're already going pretty strong. So the mission of this group is to support the understanding and adoption of artificially intelligent systems by organizations and institutions in the Northeast Ohio region. And primarily, we want to provide an open access educational resource for aspiring data science, machine learning, and AI professionals and enthusiasts in the Northeast Ohio area. We'll also be exploring other opportunities to support this mission as time goes on. Meetings will include talks mostly, research walkthroughs, project showcases, surveys of different fields in AI, and hopefully we'll maybe start some coding events next year. The content is always supposed to be accessible to newcomers, but rigorous enough that it provides value to people who have interest and who've been learning this stuff. And of course, due to the technical nature of the material, some talks are going to be suitable for a more experienced audience, but those will be designated as such on the meetup page when we have those talks. Yeah, if you'd like to speak, please contact me. Of course, preference will be shown to material that fits the guidelines that I just talked about. And if you have a topic you want to hear more about, feel free to post on the meetup group page. There are conversations that you can start, and hopefully you can find people who'd be interested in hearing the same talk, or maybe just give the talk yourself, put some slides together and send them over to me and see what we can do. Special thanks to Pandata for sponsoring tonight's event. If you want to talk about what we do, come talk to me or Ian later on. Also, thanks to Progressive for hosting. This was kind of put together last minute, and really happy that Andrew Placer helped me put this together. We're also always looking for sponsors and meeting space, so you can contact me about that. We model this part after the big data meetup, where we have a few minutes for recruiting shoutouts. So if anybody is looking for talent or is looking to find a role, you can stand up and give your spiel for a minute or two, and yeah, if anyone has anything. Okay. Pandata is actually looking for a junior data scientist and a data engineer. So if you know anyone, or if you feel comfortable applying for those positions, you can email hello@pandata.co or talk to Ian or myself. So that's it. And so tonight we have Jacob Trombetta talking about computer vision first, Nico, Lindsey talking about self-driving cars, and Ian Ferre talking about the economics of AI. So we will start that right away. I hope you enjoy everything, and thanks for coming.
Cool. Thanks, Jason. Thanks, everybody, for coming, and thanks for hearing me talk for a minute. So I'm going to introduce computer vision. So my name's Jacob Trombetta. I work as a software engineer at a place called Applied Vision, and it's down in Akron. And what we do is we inspect food and beverage containers. So we create these systems with cameras that talk to a computer, and then we detect defects in your cans or glass bottles. I went to school. I got a master's in applied mathematics, and then I sort of, from that processing, I found this job, and I've been there for the past 5 or 6 years. So, I'm going to ask you a question. How would you teach a computer how to catch something? So, say that this tennis ball. So if I threw a tennis ball to you, what would you do? So I have this tennis ball. I throw it, and what? You would react. You'd catch it. So it's like a part of you. Like you just know that process of trying to catch something. But when you think about how would you tell a computer to do it? You know? So you'd have to get a computer to see you, understand it was a ball, and then understand it's being thrown at you, and then understand to catch it. So that's with a tennis ball. Now, say I picked up a rock and I threw it at you. So there's a different process that you would automatically go through. Like if I threw this at you and I threw this at you, you'd react really quick. So, how do you teach a computer how to do this? Another thing, like a football. So say this is just a sphere. So it's a green sphere. So tell the computer, look for a green sphere, however it's tracking, I'll grab it. When you get a football, it depending on which way the football is oriented, it's a different shape. So how do you teach a computer to see this and understand it? And these are the goals of computer vision. So the goals of computer vision is to get an understanding of what you're seeing. So first, you need to see. We do this, we've evolved over millions of years, our sense of sight. And you see that there's objects. So right now, just objects. Then you have to describe what objects you're seeing. So you see a man, you see he has a tennis ball, you see he has a rock. Described it. Then you have to understand what you have seen. So I understand that I'm going to try to catch this tennis ball, and I'm going to try to get away from this rock. Now, it's neat how this stuff comes automatically, and how when you start to break it down, this problem, just how your mind works and how you learn as a kid to, catch something or move away from something. So how can we do the first part? How do we teach a computer, or how does a computer see? We have our eyes. A computer has an image sensor. So these are in your phones, a webcam, cameras on your, just any sort of camera. So right here is a picture of this is like 10-year-old image sensor, a CMOS sensor. And what it does is light reflects off a surface, and these sensors capture that light, and they produce data in the form of pixels. So pixels, you have color, RGB, so red, green, and blue. You're going to get values between 0 and 255, and this is how the computer is going to see. So this is, up on top is a picture of a cityscape from above. So think like a drone shot or real high satellite image. And if you zoom in, this is what the data, this is monochrome, single channel data. And over on the right, that's how a computer is going to see this. So if you zoomed in, the computer gets these numbers. So these numbers So when you're looking at image data that comes into you, this is an example of how pixels are distributed on different kinds of images. So these are all monochrome images, and accompanying them are their histograms. So the histogram is the pixel intensity, so 0 to 255, and the frequency is the number of times that pixel shows up in the image. Look, upper left, it's a dark image. You can see that the pixel data is all squished on the lower end of the intensity distribution. Then right below it is a brighter image. So if we just shift those pixels over, the image appears brighter. Then upper right, you spread out that histogram, and you have both light and dark pixels, and that's why you get more of a contrast. And then the low contrast image, you smush that histogram down. So this is how the pixel values, how a computer would receive this image. So seeing, we're really good at that. We're really good at giving computers this data. So once when the computer gets this data, how can it describe what it's seeing? So this is done, classically, it's done with image processing. And more recently, it's done with training neural networks, and like self-driving cars, which we'll talk about later, like how they train neural networks. You don't have to do as much image processing. So computer gets a data. So this is, a computer gets image of an MRI, like it is behind there. Great. It's those pixel data. It's, it's a value between 0 and 255. So what are some things you can do with it? So one of the things that, say you're training a neural net and you want to increase your data set that you have, you can do these transformations on an image. So you know how you resize something and it changes the way the image looks. That's classic image processing technique. So you could use it to help train a neural net. You could also use it to stitch together an image. So this is a panorama that would use that sort of translation. So it would match up, you'd do image processing, you'd match up parts of the scene, you'd stretch it or compress it. So this is an example of image processing. Another thing is edge detection. So if you had to do like a classical technique to figure out where this, like I have this ball, you might use edge detection to find out where are the objects in this space and what can you, then you have lines like you see over on the right-hand side. Then you have to figure out what to do with those lines. An interesting thing is this is what a trained neural network. So like if you were at the last month's talk, Jason introduced us to deep learning and neural nets and deep learning. So this is an image of a neural net, and this is an example of a neural net, saying that this is an Audi A7. And what's interesting is these are like layers of the neural net, and the layers of the neural net are actually really good at, you'll notice they detect edges. So you can see there's filtering and done in this layer, and you'll start to, you can find edges with the neural net, much like these edges are found here. So image processing, some examples. So in film, if you guys saw Star Wars, there was this scene in Rogue One where the actor on the left is dead, and somehow he was in the movie. So this is something that uses a lot of image processing. So if you've seen any pictures of behind the scenes, it's like all green screened, and they have like the dots on their faces. So there's a lot of stuff that goes on to, find the dots, put the old actor's face on the new actor's body. But there's so much involved. You need human intervention for the whole artistic process. So there's not really understanding that comes from this. So it's not really computer vision, but this is a really good example of image processing. Now, image processing in sports, you guys have seen this. It's a 1st and 10 system. And what it is it draws the first down line on a field. So there's a lot of image processing that goes into, drawing this line. So what they do is, it's like multiple camera systems, and they have to go and make a 3D model of every stadium before the season, which is pretty crazy. And they have like a supercomputer to draw this yellow line. And and now they have a lot more stuff. So I'm not a huge sports guy, but when I do watch it, it's like just how everything. I'm sure this is probably the least impressive example right now, because don't players move around sometimes? Like the computer. Well, the players always move around, but so those were all image processing. And image processing, the goal of it is to produce images. The goal of computer vision is to produce understanding. So it's great that you can, it's great that you can see this ball, and you can see the rock, but you need to understand how to react to the ball and to the rock. So an example of computer vision, we have computer vision in our smartphones. So the new iPhone X has the facial recognition. To unlock your phone, needs facial recognition. So the image processing step is finding the face, and however they determine where the face is. But then the computer vision part of it is the phone then unlocks because it knows it's you or it's your brother. I don't know if you saw that news article today. I know they're trying to break it. Twin brother, yeah. So how can we teach a computer to understand? There's 2 ways to do it. There's multiple ways, but 2 big ways to think about it. Top down and bottom up. So what do I mean by top down? Top down is you take preconceived notions about the data and you use that to produce understanding. So I have, back to the tennis ball, I have this green ball. You know it's green, it's a ball. And then you use that knowledge. So I'm gonna take a color image. I'm gonna try to find the guy throwing the green ball. So I'm gonna look for the green in the image. Bottom up learning is you don't have any of these preconceived notions. You just learn from the stimulus. You learn from the data. So this is like I throw a ball at a kid and they're not going to know what to do at first. It's just going to hit them or miss them. But you just keep throwing it, and then you learn how to catch. So you learn from the stimulus what the desired result is. So here's some examples. Computer vision, say, in the post office. This is one of the earliest examples of implemented convolutional neural network. And this was done to find out what letters or what numbers you wrote. Like if you have a zip code, instead of having someone look at every zip code, you have a computer do it. Now, let's think about how to solve the zip code problem top down. So we know what numbers look like, right? You know what a 3 looks like. You know what a 4 looks like, an 8. But then does your 8 look like this, or does your 4 look like this? You know, this 4 isn't connected on the top. You know, is this an 8? Is this a 9? So if we're doing a top-down approach, you would have to know, you know, have to use more 4s to try to figure out, you know, there's more logic that's involved with this. And the way they solved the problem was from a bottom up, where they taught this neural net. They have examples of numbers, large data set, and they train it. And with this trained data set, you can find out that this is 384. So it was been really successful, this example, and they're doing good with it. Computer vision in manufacturing. Now this is basically what I do for my day job. This is a picture inside a can plant. So aluminum cans. You can see there's cans up on top. So it's like multiple layers of these conveyor belts that take millions of cans. It's pretty crazy to see all of them. And then look at the names of some of these, like it'll be like Crazy J's juice. And you're just like, there's a million of these right now. Like a million of these are going to be filled and people are going to drink this. But in manufacturing, think of it, you have one can, you know you want this can to be green and gold and you know it has white letters on it. So top down, if you learn you know what a couple of these cans look like, just apply that model to, I want to know, does this can look like you know the other million cans that went through? If the green's gone, you know it doesn't look like it, kick it out. And the top-down approach is actually really successful at this. You know, you have same example of something coming through cylindrical can, and you need very little data, and you can start working on, you know, understanding, should it be, is it or like can they fill it with their Crazy J juice? Another interesting computer vision topic is computer vision with memory. So if you teach something to understand, it can understand that you have these letters, you know, or these numbers. That's cool. But how do you teach it? So something like this is that, you know, that game where you have the cards, you flip them around, and you have to find, you know, which ones match. So which 2 carrots match. So a way to do this, you know, traditional top-down approach, I don't know how you would really approach this problem other than, I guess you almost would have to take a picture of everything and remember it, and couldn't apply it to anywhere else. But you can use with machine learning, and hopefully later topics we'll talk about recurrent learning, so recurrent neural networks. And what these do, these recurrent neural nets learn from the past, and they have their computer vision with memory. So they're used, you know, this is a trivial example, but they'd be used to, say, if you're watching a movie and it's trying to describe the scenes in the movie, it takes context from previous scenes and applies it to current scenes. Now, computer vision in your car. So let's think of the top-down, bottom-up approach. So right now, you know, the computer can see this because it can take a picture of it with this, you know, with this camera. It can understand that it could just describe some of the things in the scene as, you know, sky, people, cars, bikes. And when it tries to understand, if you try to think of this problem in terms of top down, you have to teach it like whatever, you know, what do people look like? So this is a person, but then you have a person on a bike. You have a person, you know, in a dress. You have, you know, you have tiny people in the background. They're walking whichever way. You have cars, you have bikes. So top-down approach would almost be impossible for a self-driving car. So bottom-up approach, which the next talk we'll dive into more, is to train this car from, you know, you have images of people, you have images of, you know, you have driving data. You're driving around and it learns from this data. It learns from the stimulus you give it how to drive in the world. So that's basically, to understand, so in summary, computer vision is understanding of the world around you. So it's not necessarily image processing. Image processing just makes images. But the idea of computer vision is to understand what those images are. So if anybody has any questions or comments, I would love to answer.
Early on in one of your slides, you had the three images, and then you got the matrix of base 10 numbers.
Yes.
Now, you said the computer was seeing those numbers there. Computers work in base 2, of course, so there must be a conversion there going on for it to do that.
Right, and actually, oops, I'm glad you brought that up. So the question, so these pixels right here, computers, the reason it goes from 0 to 255 is 8-bit. So for this, and you can get higher bit rates on cameras. So this one, like where I typically work every day, it's just 0 to 255, and then because it's, you know, 8-bit for in, you know, base 2. And what a lot of so when you're doing any, like if you're training a neural net or stuff, typically what you do is you normalize this data, so it's between 0 and 1, and then you can get a floating point representation of that between the 0 and 1, or -1 and 1. So you'll do that a lot when you train in AI. You'll do a lot of normalization of this data. Yes.
In the canning QA example, you said you work top down, teach it all the features to expect on a specific type of can, circle, yellow letter,
Right.
whatever. For just a general QA type application, wouldn't they bottom up or train? A good example of that, supervised learning, wouldn't that be a more general solution, or is it hard to figure out all the ways things can go wrong?
So it's interesting. I feel like there could be the top or bottom up learning could be applied to the field for sure, and needs to be applied. What I find is most people do the top down because you have so many different kinds of cans, and they just, the kind of defects they want to inspect have, I guess, sort of known areas. I guess the tools that they developed were before we could really train a neural net very well and very fast. So they've kind of just used these filtering techniques.
That's legacy, basically.
Right, yeah.
Okay.
So in your craft, after the computer has detected a defective can or bottle, what happens then? Is there an actuator that pulls that out, or a person pulls it out, or what?
Air just like kicks it out. So they go real fast. It's like 3,000 cans a minute. So like blowing by, and then it'll be like, so. And then in glass plants, they go slower, but they just kick it out and break. So, but I don't know if anybody's been to a glass plant. It's like it's like molten glass flying everywhere, and it's really crazy. Anyway, I'm sorry.
Oh, the recruit that with memory.
Yes.
Always use a bottom-up approach. Because you're building up memory.
Right. Yeah. Yeah. To train that neural net. Yeah. It would be. So Jason's like, that's sort of his jam, right? The recurrent neural networks stuff with.
I've done it.
Yeah. Yeah. So he would be the one to talk to you about that, the memory stuff. Yes.
How about a more complex scene such as printed circuit board inspection with machine vision?
That's what, if they're all going to be similar, I think you could use sort of the same approach as the manufacturing. You know, you learn a few of them, and then from that, you have a few examples of it, and then from that you can start inspecting those. But that's a great question. Cool. Any other questions? Well, thank you guys for listening. My info is on the bottom here, and I think the slides will be available. So if you want to get a hold of me, please feel free.
Have resources?
Oh yeah, I do. Thanks. So these are some. So in my journey to learn artificial intelligence, deep learning, and image processing, I've used a lot of the massively open online courses, and this slide has all the links to it, and I think they'll be available.
Yes.
So these will be available to you. These are ones I really like. There's also Udacity's artificial intelligence degree is how I met Jason, and it's a really cool degree. And then I also have some links that I used for making this paper or making this presentation. So, and then there's a recurrent neural network with deep learning specifically for computer vision. Okay. Cool. Well, thank you guys.
Cool. Yeah.
I don't know if you gotta
Yeah, I'll do it.
open up different stuff. I did make an offline copy too.
I think this should be good.
All right. Oops, I can't see it. Gonna minimize this stuff. You Mac users.
Oh,
Yeah,
what are you looking for?
Oh, the slides, just so I can read along with. Oh, I guess they're right there too.
Yeah.
Okay. Okay. All right, guys. I'm going to talk about autonomous self-driving cars. I have a hard time saying autonomous for whatever reasons, but anyways, I'm talking about self-driving cars and the use cases, how they use computer visions in some of them. I'm going to talk about a breadth of things, a wide breadth. I'm not going to get super deep or anything, because I'm a beginner in a lot of these things myself. Who am I? My name is Nico Lindsey. I work for a company called Embrace Pet Insurance. I spend about 2/3 of my time doing standard software development stuff, and the other third I've been doing machine learning stuff. I'm kind of new to the world. About a year and a half ago, 2 years ago, I started just like he did. A lot of you guys are doing. I took some online courses from Coursera, and I got into it, liked it, started putting production models at work, and it's a big hit. Udacity is where I took the self-driving car engineering course. I really like it, heavily recommend it. It could be pretty tough, it's you got to work through it. As you can imagine, Embrace Pet Insurance does not have a self-driving car division yet. My email is up there, nicolindsey@gmail.com. Feel free to shoot me any questions or whatever, contact me. I'll have that at the end too. All right. So self-driving cars have levels that they identify how self-driving are they, right? Level 0, no assistance. That's what most of us have today. If you've got a car in the last year or two, they might have something a little fancy on it, but level 0 is nothing. Level 1, cars help you with one task at a time. That one task might be something like adaptive cruise control, where the speed slows up and speeds up and slows down based on the traffic around you. Another example of that might be emergency braking. Car sees you're about to hit somebody, slams on the brake. It's helped you with one thing at one time. That's level 1. So there actually are a fair amount of those things out there right now. Level 2, they call that hands off, eyes on. Because now the car helps you with two things. Tesla's autopilot, not their enhanced autopilot, but their autopilot is a level 2. So you get that adaptive cruise control, and now it can maintain the same lane. So you don't need your hands to drive. And I should say level 1, 2, and 3, they're all sort of restricted to road types, usually the highways. So level 2, hands off, eyes on. Level 3, there's arguments if Tesla's enhanced autopilot's level 3 or not, but I say it is. But it's hands off, eyes off. Level 3, not only do you get the adaptive cruise control type feature, and it stays in the same lane, the car is now smart enough to intelligently pass people and stuff on the highway. So now switches lanes and takes care of that. So they say that's hands off, eyes off. A lot of companies are skipping this one because in level 3, an emergency situation, you still require the driver to take over. So you've trained this driver to say it's okay to go play at your phone and not pay attention to the road, but you still have to take over in an emergency situation. That's a big problem. So a lot of companies are saying, let's just skip this and move to level 4. Level 4, mind off. Full self-driving cars. It does everything for you, but it's in a geo-fenced area. So maybe something like the city of Cleveland is certified level 4. So you get there and you don't need a driver, you don't need a steering wheel, and inside that city, that car can go anywhere you want. Literally yesterday, Waymo, which is a Google self-driving car company in Chandler, Arizona, have their cars out there driving now without the drivers in the front seat. They still have an emergency driver in there. They kind of have an asterisk in those articles, like, oh, there's still somebody there sitting in the back seat by a big red button that says pull over. They don't really say that, but there is still somebody there in emergency situations. But you call up these vans, and that's what this picture is up here, and you say, okay, come pick me up, take me to this other place. And in that geo-fenced area, that's why I call it level 4, it can do everything without somebody behind the wheel. And ever since this happened, if you start looking up stories on like self-driving cars, and I have a Google phone, and the Google Assistant gives you stories like it sees you're looking at and recommends you more. It is just a domino effect. Google came out and said this. Now everybody else is like, oh, we're here, we're doing this now. We're doing this in London, we're doing this in Europe. It's just, everybody's like announcing their stuff right now. You start following the news, it's just so hard to keep up with. There's so much happening. And level 5 is fully self-driving everywhere, no restrictions, no geofence. It can drive on the side of the mountain. This is when you don't have steering wheels. Maybe cars are being redesigned. I don't know. Maybe everybody's looking at each other in the middle. I don't know. I can imagine designs of cars being way different. Federal government is actually, I went to GTC, which is a NVIDIA GPU conference in DC last week. Great conference. And I was talking to this random guy, and he's like, oh, I'm the lobbyist for the self-driving car group. Just like a random conversations, but they're trying to move the restriction from requiring the steering wheel hardware in cars. So like that's already being worked on. Interesting enough, he says politicians are actually really, really into this technology, and he's seen very little like restrictions on it. I didn't expect that. And timelines. So I wrote this model year 2023, but in reality, like I said, Waymo's out there right now. Any car you bought from Tesla in the last probably about a year, they're seeding the market with the hardware already for it. So they're just working out the kinks with the software. They've come out and said early 2019 they'll be ready to go full level 5. And then a lot of car companies are Cruise is this other car company. This is actually GM. They picked up this company for billions of dollars, whatever, and they think they're going to be ready to go by 2021. the industry has this date called like model year 2023, where like those cars you go buy from GM or Volkswagen, Ford, they're all going to be ready to go. So that's like the year everybody. And normally people are a little pessimistic on these predictions, but it sounds like they're moving faster than they thought they were going to. I don't work in the industry, but when I talk to these people and I go to these like AI conferences, they're chugging along. Like they almost got this. I saw a demo of NVIDIA's self-driving car system driving through like 3 inches of snow flawlessly. It's like, well, that's the thing everybody says, like how well is it going to deal with snow and rain? It does well. So some of the hardware requirement, I'm going to talk more about, there's kind of two different philosophies if you start looking at hardware. And mostly I'm going to talk about Tesla here at first because, well, they're a cool company, right? But Tesla, I say, their philosophy is kind of a camera-first philosophy. These cameras, they have a good distance. They see 200, 250 meters, but they are sensitive to weather, you know, rain, fog, snow. That does affect how well these things work, but they're pretty cheap. These Teslas have 8 cameras around it. I'm not exactly sure where they're placed. If I was a betting man, though, every car, every place around that car on the outside can be seen by 2 cameras. Because if you can see 2 cameras, you can do stereo and you can measure depth. And that's what you really need to know, is how far away stuff is from you. The next thing they have are these ultrasonic sensors. You see these on the cars a lot, these little like buttons on the side. These are just sending sound waves bouncing off and letting people know how far away things are from them. They've got a pretty short distance, but their job is to tell you if there's somebody in the lane next to you. Or when you're backing up a car and it's beeping, that their job's to tell you you're not going to run somebody over. I don't know if they have too much of a weather effect. Their range is so small, but they're dirt cheap. If you've ever done any Arduino work, you can get these things for like a couple bucks. I think the Teslas have like 12 of those around them. They're just like, put them everywhere. Radar, instead of bouncing sound waves, now bouncing radio waves. Teslas have a front-facing radar. That's it. Their radar is really good, though. Radar range, depending on the type of radar you buy, can vary from 300 meters to 200, from 30 to 200, and maybe even more for long-range radar. And they're pretty cheap. Radars can penetrate snow. I mean, not snow, but actually, I know they can fog and rain. They do a good job. But Tesla said their radar is so good now, they can bounce it off the car in front of you and read information about the car in front of it and send it back. I thought that was pretty cool. And GPS is not going to tell you to stay in your lane. If you have a 1 meter error rate on a GPS, it's not going to help you. So it's just kind of used for navigation right now, and it's sensitive to like cities. I guess buildings block GPS all the time. You go in a tunnel, it disappears. But I did see demos of new versions of GPS. Instead of having like a meter, 2 meter accuracy error, it's now like centimeters. But it requires these towers all over the place. It's a pretty expensive deploy. If I was a betting man, they're never going to use GPS to keep you in your lane. So these are the main things like a Tesla has. All the other companies seem to have LiDAR first philosophies. And you can see right away why Tesla isn't going with the LiDAR first. They are uber expensive. It's a company, I think it's called Valentine. They're sort of the leader in this market right now. And they make a hockey puck one, which is their new affordable one. And that was $7,999. So you can bet if Tesla's buying that for $8,000, they're selling it to you for $12,000. It's just not affordable. Now in the future, they have these solid state LiDARs and they have other things that's supposed to take manufacturing cost to a couple $100s, but they're not there. And Tesla doesn't want to wait. They want to put their stuff out there now. So they don't do that. And then you have the brains of their operation. Yeah. LiDAR, okay. LiDAR, basically you have a stack of 2 things. You have one stack of lasers that spin around really, really fast. And underneath that, you have a stack of mirrors that just throws the radar, just the laser shoots, bounces off something, and hits these mirrors. And then they measure the differences. And that gives you the best view of the world around you. I mean, it's a great technology. And it sends you gigs of information, like just all kinds of information. I should have included a shot of like what it sees, but it's powerful stuff. But it's just, instead of bouncing radio waves or sound waves, it's now bouncing light waves. So the computers, they don't really release these things. I have copied and pasted. They really don't have a distance measurement either. But at that conference I went to last week, they had the upper left-hand corner. That is the Drive PX2 made by NVIDIA. It's what a lot of companies are using now. And in the lower left-hand corner, they have their Pegasus unit. So the Pegasus units apparently shipping to manufacturers in mid next year. The Drive PX2, in 1 year, when you go from the PX2, the Pegasus increased it tenfold. In 1 year, they improved performance 10. And the Pegasus is what they're selling as their computer. They say it's as powerful as 15 racks and a server the size of a license plate. They're just processed. They've got a couple of GPUs on them. They're pretty impressive things, and 500 watts of power. And then there's that one in the middle. It's the same thing as a Pegasus, just a smaller version, and maybe it's made for like level 3 instead of level 5. Okay, all right. So let's get to the computer vision part. Where are some things you might use in computer vision in these self-driving cars? Lane detection, obvious one. Vehicle identification, traffic sign classification, behavior cloning. I'm going to talk fast about these other things. I want to get to behavior cloning because it's my favorite, of course. So lane detection. This is going to overlap a little bit with what we heard in the first presentation, and that's good. So we get this image, and remember, these cameras are taking 30 frames per second. So you're getting 30 of these images per second. We have to do all this in real time, and we have to process all those sensors, and we have 8 cameras. That's why you need like these supercomputers to do it. So I'm getting this image, and the first thing I need to do is make it a grayscale. And oops, I'm gonna let myself. If you used OpenCV at all, like these are literally 1 or 2 line commands. They're pretty quick. So you grayscale the image, and then you put a mask on it. I don't have a picture of the mask, but in reality, we don't really care about the whole image. We really only care about the road in front of us. So you draw a little mask on the road. Maybe it's a little triangle that goes from lane to lane and kind of peaks in the middle, something like that. And we kind of throw out the bridge. We don't really care about the stuff on the left and right. So you have a mask there. And then you're going to do the edge detection you talked about. And this is canny edge detection that I'm using in this particular case. And edge detection works, it's just trying to find where there's a sharp difference in colors. And I really like this histogram plotted right on here, because you can see that the there's a sharp change in color, and it changes, and it goes, and then it hits that middle line. There's a sharp change, and then goes, and then there's a sharp change again. And it's just looking for that difference, and then it's going to draw lines on it. And remember, in reality, I have this mask on this picture, so I'm only looking like at I don't know, a third of the picture, maybe a half of the picture. I've already thrown out the lane to the left and to the right. So if you look at it, you can pretty easily tell in this graph where the 2 lines are for the lanes. And that's the picture that you kind of get as your output for the canny edge detection. And then you do something called a Hughes transform. I'm not going to get into that, but it's basically turning a bunch of points into a line, and then you can plot your line on top of it. So now you can see the lines right on it. This, in the class I took, a lot of the stuff I'm talking, it comes from the self-driving car course. This was what I'd call the easy lane finding. After we did this, towards the end of the semester, we did a advanced lane finding, and you'll see why in a second. So in this video, here we go, maybe, there we go. In this video, you can see it's working pretty well, actually. You can kind of see where it peaks on the left. It's because I told the mask to stop working. But it's doing a pretty okay job there. But I told you that that was the easy lane finding. And next slide, please. Yeah, well, I guess there's a navigation here, maybe. There we go. And because little things can throw off this edge detection stuff. No entries found. The computer's yelling at me. I'll just close that and hit play again. Yeah, it's searching something in the dictionary. I don't know what I did. But you can see when the video plays, you can, it gets kind of crazy. apparently you just have to hit the button. But if you look in the middle of that lane, there's like a line in the middle, and it's probably detecting that as an edge, and it's just making things all kinds of weird. So not something you want to put in a car, but it was a fun academic experiment to do it. So we need to make it better. Before I show you quite how to make it better, every camera has a little distortion, and you use these checkerboard patterns to correct for this distortion. No camera's perfect, and the original image on the left is just a camera taking a picture of a checkerboard. You can see in the upper left-hand corner that square is bigger than like the one in the middle. There's a little bit of a bubble out. So with OpenCV, you just like give it some points and say on distorted and makes it flat. So that's what it did there. And here you can sort of see the this hood here in the original image kind of goes straight across, but in the on distorted image is a little bit of a different shape. It's flattened out a little bit. It's kind of harder to see in this picture, but you can see how it flattened the bubble out in the little one. So my whole point is to walk into this one. So to make lane finding better, we on distort the image, and then we do a different type of edge detection. There's multiple kinds of edge detections, but it kind of does the same thing. It makes these points, and you can change the sensitivity and the threshold, and you still have that mask on top of it. And now what I do here, the fun part is I'm looking at this, I cut out my mask, and now I'm going to warp my perspective. So instead of looking at the picture like this, I'm going to do a bird's eye view. And that's exactly what's here. If you, yeah, okay, you can see my mouse. You can see like this is this lane, just bird's eye view with these dots. Same thing, this lane, bird's eye view here. And once I do that bird's eye view, I can now connect the dots, make lines, and fill it up. Fill it in with this little green thing. And then I take that warp thing and I go, okay, I don't want to be a bird's eye view, and I flatten it out, and then I put it in a final image. Some things like this, see how it's got this big bubble in here, probably detected too much stuff here. Well, you can actually smooth those out, because remember, I'm getting 30 of these a second, or however fast the camera is, right? Well, I can maybe average 5 of those frames together to get a smoother picture. So, and that looks it went back. I don't know what the trick is to making it play. Do you hit enter? Yeah.
You have to be in.
Okay.
In the
Okay. So you can see this is actually working pretty well. Driving down the road, it's definitely prettier than the 2 lines. It's making curves. It works fairly well. It's still not perfect though, because if we put it in a scenario like, don't want to watch the whole video. Okay. You can see it's not perfect. And this road, if you look in the middle of it, has that like a crease that it's probably detecting as an edge, and it's getting a little funky. So there's things you can adjust the sensitivity of like those edge connections to maybe work around that. But it's not good, but it's definitely better. Yeah, next slide. Okay. So that's kind of lane detection. The next thing is vehicle detection. I don't have any videos of this, but I can talk about it real quick. Basically, there's these data sets out there. I think one of them is called like the KITT data set, K-I-T-T. I don't remember. I think it's an acronym for something. But it's a data set of like, here's a car, here's a truck, whatever. And then you take it in there, you make a convolution or neural network, which is all the rage. And then it's like, okay, I know what a car is, and I can put it into this thing, and it'll tell me if this thing's a car. And that's all you do. But you don't run it on the whole, you don't give it the whole image. You kind of do a sliding window. So pretend, if you're looking at it, imagine like a 10 by 10 grid on top of that layer, that image. So I'm going to check that first thing and say, oh, is there a car in this first one? No. Now move over. Is there a car in this one? No. Move it over. Is there a car in this one? No. Move it over. So I'm kind of scanning this image. And remember, you're doing this like for 30 pictures a second, multiple times on an image. I guess these computers have to be pretty amazing. And then what happens, you end up with a picture like on the left here. And you see how there's multiple bounding boxes drawn? Well, that's because maybe on the first sliding window it detected a car, and the second sliding window it detected a car, so they're overlapping windows that detected a car twice. And to fix that, you can use something called a heat map, which is built in right into OpenCV, and it kind of tells you where there's a density of a lot of those things. And then you can just say, okay, I just want one bounding box around where it's most dense. Okay, behavior cloning. So NVIDIA has this card called the BB-8. And what they did with it is they just have cameras. They have nothing else on it. And they just drive around and they're gathering data. And they have an image. And then they're gathering like what the steering angle is for that image. And maybe like acceleration, some other facts for the car. So it's just like a big CSV file with 3 or 4 images inside of it. And then stats about the car at that moment in time. And they released a paper on this. And the paper, it's a good read. It's actually much more readable than you might think it is. And inside of it, they showed this network. And the only reason I'm showing this, I know this is a beginner's, but like I kind of want to show you what's inside the paper and what you do. Because like I'm not coming up with that thing on my own. I'm going to look at published things, and I'm going to just twiddle with it, mess with it a little bit, tweak it to my likings. But that's already out there. I'm going to use it. And comma.ai makes one has a good model out there that I've used. But this is one made by NVIDIA. And I also want to show you, because I know if I'm sitting there, I was like, okay, that looks nice, but how do we actually use it? This might be what it looks like in code. I don't know how readable it is out there, but this is Keras on top of TensorFlow. And this is, yeah, I think it's this mapped to that. And you can see it's not really that much code to make a neural network. It's not. You got to know how to tweak the parameters and stuff in it a little bit. But like a convolution on the left, I just said it's 2D convolution on the right. It's just figuring out the syntax. It was much easier once you, and I will say Keras does make TensorFlow much more usable for me. So in this class, they have a simulator, and it's going to do basically what I described the BB-8 car does. Oh, I didn't get fully into the BB-8 car that NVIDIA has. They trained this car in San Francisco. They drove it hundreds of miles, right? And then they sent this model to New Jersey. And they said the car was able to drive in 90% of all situations in New Jersey. It's never seen New Jersey, but it was able to do it. And it was just behavioral cloning techniques. So I have this simulator, and I drive around. Maybe I should pause it because this is the result of it. Anyways, so I'm driving around. It's capturing just one camera. Just one camera. There's multiple cameras you can do. And I'm setting the throttle. I don't care about throttle. So I'm capturing a camera and steering angle. And I drive 5 laps around this thing. I drive 3 laps like a normal person, as good as I can. And then I drive 2 laps just like a drunken fool. And you need to do that because, like, if I'm driving perfect and I want this car to drive itself and it hits a yellow line, it's only seen how to drive perfect. It doesn't know how to recover. So you have to teach it how to recover. So you just kind of weave in and out and fix yourself and get back there. And once you do that, things become much better. And then I take this model. It's a JSON file that links to, you know, all your weights and things. And now this thing can call it. Can drive itself around the simulator now with just 5 laps. You know, it took 10 minutes arriving, and now it just drives itself all the way around. On the left side, you can see it spit. I guess that's pretty unreadable, but it's spitting out. Those are steering angles. So all I'm doing is taking an image, I'm throwing it in something, I'm getting a prediction of what my steering angle should be given that current picture. And it's just doing it nonstop. A little bit, but it's fixing itself, right? And it wouldn't have done that unless I drove poorly for 2 laps. And here's the best part, apparently. Next slide. So data science, machine learning, what are the one things you never do? You don't test on your training set. Don't do that, okay? So, but that's essentially what I just did there. I don't know how accurate my model is. So what I did is I took my model and I put it in track 2. It's never seen track 2. And track 2 is actually a much more difficult track because track 1 didn't have any shadows. It didn't have these little guards on the right side. It didn't have leaves. Now, when you're building your model, you're adjusting your images, you're putting random shadows in it. Like he showed how you turn the image. You can make one image multiple images when you train it because you just augment it some. And one of those augmentations, you can add random shadows. So it's kind of seen random shadows. It's never seen a hill before. This throttle is like set at a speed. I set it slow just so it would work better, but that's why it's having a slow time going up the hill. But it's able to drive itself around this thing that it's never seen before. I was pretty happy when I got that to work. Well, doesn't care much about that. Yes.
This is like a novice driver, okay? It's like teaching a teenager how to drive.
Right. And so as far as things I want to talk about today, that's pretty much the extent. I would say that there is actually a community out there in some of these bigger cities like Austin and New York, and they get together and they build these robocars using behavior cloning techniques. And you can build them yourself for about $200 for parts you buy off Amazon. But they get together like once a month and they put a track down with some gaffer tape and they train the cars in the morning and then they race them against each other. And they're all using that sort of behavior cloning technique I've talked about. You can add other things to it, but it's going to cost more. But
is this a Raspberry Pi?
Yep, it's a Raspberry Pi on it. A Raspberry Pi is good enough for this.
Wow.
If you want to start doing more with, like, you want a piece of LiDAR or something on it, NVIDIA makes a developer kit called the Jetson. It's actually, it looks like the size of about maybe a credit card or two, but then they put it on this like mini ATX board, so it actually ends up being a little bit bigger. If anybody has any interest in doing this, though, you know, you want to like put a car together, I'd be more than willing to set up a meetup to, you know, experiment and play with these sort of things. I talked to, when I was at an AR conference in San Francisco, the guy who created Google Lens, he was there. He's a really cool guy, and he does this like once a month. So that's how I found out they existed. He was showing images of it, and it looked like a blast. So if you have any, you know, want to do that, just shoot me an email or let me know. I'll write down your name, and if there's enough interest, I'll start up a meetup and we can try it. So that's what I got. Any questions? I'll do my best. Yeah.
On the lane detection, the more advanced version of it, does that require 2 cameras in order to get the depth to go to bird's eye view? So no, you can. It only requires 1 camera. The switch perspective, it's just like 1 line of code inside of OpenCV. A perspective warp. Yeah, so I was trying to think if I used 2 cameras, but no, there's only 1 camera. And if you calibrate 1 camera, you can make it measure depth, but obviously 2 cameras, you need less calibrations and it's better. Does it use historical information or take a single frame?
Nope, just single frame. You can do it with any picture you have. You can put it in there and it'll do that bird's eye perspective view of it. Yeah.
Were all the videos just using cutting edge detection?
Well, in the behavior cloning one, for instance, I mean, there's nothing in there besides pure images tied to, but the lane detection ones, the first set used canny edge detection. If I remember right, the second one did like, what is it, the Sobol? Yeah. Yeah. So, but you got to, you know, you tweak it, you play with the parameters constantly, but it worked pretty well. Yeah.
How do you improve it? I mean, is there some sort of reinforced learning? Some way of saying, okay, this is what you did. Now this is how I would have done it differently.
Yeah, you just, you know, you just collect more data. Yeah, that's it. I mean, that's every car company is trying to do this. They always brag about how many millions of miles. And I said earlier that but Tesla's seeding the market. They are seeding the market with all their hardware, but the reason why it's not there because they don't quite have enough data. Their cameras are still capturing the data and sending it home, though. They're getting all the data from every Tesla made. They're watching everywhere you go. Yeah.
So 2 questions. You mentioned LiDAR and radar and lasers. Is anybody just listening? Because a lot of there are horns. There are people who shout.
Yeah.
Putting microphones on.
I haven't heard of anybody do it, but I heard somebody talking about this sort of thing. Like, we need to drive cars like humans do, and humans use more than 1 sense. Their argument was like, that's why we'll always need more than 1 thing to drive the car. But maybe that's a good one. I don't know of anybody doing it.
But that goes against kind of the foundations of machine learning. Computers learn differently than people. And so having that kind of sensory input is not the same for a computer as it is for us, for example.
Sure.
So the learning is completely different.
Yeah, but that doesn't mean sound isn't important.
Yeah, is there any sensor fusion ever going on? Is it just only visual or only or is this?
Oh, there's definitely central fusion. They do like these Kalman filters to pack everything together and determine like, you know, predicting where things go. But yeah, they fuse all these things together. Yeah.
My other question was, I live across the street from an elementary school.
Uh-huh.
And every day at 3:20, I mean, there's little kids, there's dogs, there's bicycles, there's the crossing guard with a stop sign. It's not really a stop sign because other stop signs you stop and then you go, but when she's got a stop sign, you just stop until she waves you on.
Hmm?
How are cars ever going to understand?
Oh, it knows that. That actually doesn't strike me as a hard problem. When I see like these lidars going off, they're seeing they know how far away these people are in front of them. You see, they had a cool demo NVIDIA does where they had this like line that showed like spaces in front of them, and all of a sudden that space goes down to 0, and they know when things are happening. Like I don't think that's gonna be an issue.
A car that makes eye contact with
Yeah.
All right. Any other questions? We're gonna have to forward. I'm sure I'll stick around, and you can.
You were mentioning the data going back. I read Tesla is getting 1 million miles a day.
Yeah. It's incredible. And like the size of it, like the LiDAR data is gigs. It's so big.
All right, guys. I'm sure he'll be sticking around. So if you have any more questions for him, you can, after the talk, we'll do that. We're gonna take a 5-minute break and then resume, and then Ian's gonna talk about the economics of AI. Thanks.
Thanks. You know what? Oh, Mike. Oh, no. Sure. Yeah, I just do a bunch of things. So they're taking like all these companies. There's really yeah, they did, you know, but apparently 8 seconds or more. Yeah, yeah, not only that, but like they're also watching. I heard like it was
Yeah. So what kind of networks were used to learn your tracks?
I use that network, which you know has like
Earth stations.
a couple of layers.
I would have to drive down to Shaker Square and burn gas.
Okay.
All that.
So you're basically playing 30 frames a second into the phone network that's running from that.
Well, it's crazy how much power these things take. Because you're doing that with a camera. That's why you need to.
Is there any open source data for all that?
video tracking while training interviews, or did you just collect it on your own?
Well, like obviously, I brought the simulator. And simulator is also their open source. Yep, that simulator is open source. You Google Udacity simulator. Okay, so I don't even have to sign up for the course.
Nope,
you don't have access to that.
I know.
Yeah, I've seen several of them. And I kind of want to do it too. You're gonna see cars on the road. Right, the shop, right. There's like a little bit that's what's so neat about this behavior technology. You don't have to check, you just let it be your tolerance.
Well, that's how.
Yeah. And that's what I tell people, like, when I step on, like, we just keep going fast. That's all we need to do.
There's only, I mean, people aren't gonna drive it. Like, you know, like people say in a car where I'm like, it's already safe for the people. Well, yeah, but like that's assuming people are rational.
I think they get distracted. Your computer doesn't get distracted. That's what I think.
But the fear is that people want like
they think that they're rational.
But they're not rational.
Yeah.
Like 5,000 people died in self-driving cars.
Unbelievable.
A lot of it. Actually, the traffic sign one I did worked similar cars, but it was sure. But it worked well for European tracks.
Yeah, it's another.
So yeah, this training data here works over there too. A lot of it does. But that is actually no, that's what you just flip okay. But like India is where it's crazy. So that's what they're
Just I got into this with my father my girls.
And I started researching, just like anything. There's a 95% chance in
things like driving a car with but it's actually other types of machine learning that are much more to do with. And I would, if you asked me how long was it good for that was part of it. So they would have said this was 40 years.
Right. It just
and other things that seem
oh yeah, Voltas are never. They had those. They had one issue. They had like they had conservative. It is over that particular road. Yeah. If you're the microphone, it's cheaper. So yeah, you can find those.
30 frames a second, but on the whole thing.
There are type of languages. Now you're not. I heard it. Yeah. But you're not
All right. I think we're going to start back up. So yeah, we are going to talk about the economics of AI. Ian Ferre, Pandata is here to talk about that. I think this ties in nicely with the talk with self-driving cars, not only because of the impact that self-driving cars will have one day on the economy, but also it ties into the levels of self-driving cars and the predictions that people are making about when these things are going to be fully autonomous. There's a lot going on. Historically, there's been cycles of AI where hype grows, funding floods in, and then research happens, and promises are made, and promises are not kept, and people are disappointed. You know, these $1 million projects just don't show up any results, and soon enough, the funding crashes, the hype dies, and progress slows. And that's happened like 3 or 4 times in the past 50 years since AI was founded. But we're going to talk about, you know, what happens if this trend continues for the next 20 years or so. And hope you enjoy it.
Thank you, Jason. So hi, everybody. My name is Ian Ferre, and I'm going to talk about the economics of artificial intelligence. Make sure okay. So before I really dive into it, just a little bit about myself and my background. I went to Case Western Reserve University and got my BS in Math and Economics. While I was there, I started a company called Greenlight Technologies, and we had this goal of bringing efficient, sustainable power to developing countries. However, the price of solar panels just kept going down and down, which was a great thing because it meant I didn't have to keep working at that company. So I actually got to pivot entirely what I was doing, focusing on energy and get into data science. So I became a data analyst intern at the Cleveland Clinic for a while. I was part of the finance division down in Independence, Ohio. I got to do some really cool modeling there, and because of that, I actually met the founder of Pandata, and I became the first employee there. So that's where I work now. I get to work with Jason. We get to work on a lot of really cool stuff. But I'm still in love with economics. So when Jason gave me the opportunity to talk about it, I had to jump on it. So I was really excited to kind of get back into the economics world for a little bit. So to start off, I just want to talk about a couple examples. So we're gonna go way back, and we're gonna talk about the Luddite movement. So for those of you who don't know, the Luddites were a group of textile workers and weavers who were highly skilled, but really worried about new emerging technologies that were basically automating them out of jobs. They were really worried that they would become obsolete due to the emergence of new ways to craft textiles using machines and the ability of low-skill workers to use those machines and replace them. So they actually led a movement for about 5 years throughout the Nottingham region of England, and they eventually caused enough damage to factories and machines that the government stepped in, the military stepped in, and essentially ended a rebellion. And this is the first time in history that we really see people protesting against automation. You don't see people protesting against the wheel. You don't see people being like, I don't want this spear, like it does help. But this time people were like, okay, this really affects our livelihoods. We don't want it, get it out. And it didn't work because manufacturers were like, hey, this makes our good 10 times cheaper. We're gonna go with it. And we don't see another protest like that again, actually, pretty much ever. I kind of believe we will. So that prefaces where this talk is going to go. So another example, a little bit later, we see automation come to America pretty heavily in the agricultural sector. In 1900, we had about 40% of workers employed in the agricultural sector. And due to just changes in technology, even tractors, we could increase the output of every single farm. One farmer could handle a lot more land, and we just didn't need as much staff. So we saw a decrease from 40% in 1900 to now we're at 1.6 to 1.8. The number's a little fuzzy, percent employment in the agricultural sector, which that's a huge reduction. So these displaced workers moved to industry and services. So since about 1950, though, we've started seeing the same trend, the same decline in the manufacturing or in the industry sector, right? So we're starting to see manufacturing jobs just be robots that are moving around and building cars. Coal mines, a lot of that is now automated, and we're seeing this downward trend there as well. And this is not throughout the United States. These numbers specifically are, but this is a trend across developed nations worldwide. So the two examples I've talked about so far are examples of first order automation. So with the Luddites in 19th century England, we were replacing handiwork and the skill of these crafters for machine consistency and the ability of low skill workers to make as quality of a product. For farming, it was mostly replacing muscle with mechanical power. Other first automation is logic for digital calculation, so just calculators. So other items include cars that are not self-driving, tractors, computers, even continuous process manufacturing. So like the whole conveyor belts and people jumping in and out. So then comes second order automation. This is where machine learning really comes into play. And we start kind of automating a higher level of human intellect or human function. And these are ones that can see, they can talk, they can listen, they can make decisions based on specific situations. So self-driving cars would be a perfect example of this. Things like Waze, the map system that continuously reroutes you because traffic happened or there was an accident, 10 blocks ahead, hey, go around. That's situational adaptability. Tesla, a great example of vision. Google Translate, Alexa, those both have language recognition. There's a million of these products coming out now. And then so finally there is third order automation. And third order automation is it's the strong AI. It's capturing the human essence as we think of it. And it's typically what we see play out in movies or dystopian films. And the world is basically either going to end in Terminator or an Iron Giant comes along and everybody's happy. We'll see. So to understand how the new wave of artificial intelligence is going to affect us, it's a good footing to go back and just look at how first order automation kind of changed our economy. So going back to the Luddites, and this is, I promise, is there's only a couple slides of economic charts, which I know most people can't stand. Personally, I like them. So the Luddites were eventually replaced by these low-skilled workers and assisted by technology. So the price of these textile goods actually decreased, and this increased the quantity supplied. So you have a lower price, but more people have access to them and can afford them. So this creates a consumer surplus. So consumers benefit when automation like this occurs, because now there is more capital in my pocket. If I used to buy the textiles anyway, but now they're cheaper, cool, I've got all this extra money. What am I going to do? I'm going to go to the bar. I'm going to go buy a scarf that goes with my clothing anyway. I'm going to go buy some new shoes, whatever it may be. I have more money. I can go spend it. And all of these additional goods I'm buying, now they need more labor. So they're going to hire a lot more people. But the main issue is that it might not be the same people. It might not be that weavers and textile manufacturers are great at pivoting into serving bar. So this has generally been proven to be true across almost all first order automation we've seen. Labor typically increases when technology can assist in the workforce. But so we need 3 kind of assumptions to be true. That is people are mobile. So if I automate a factory in Pennsylvania, I need if those people want to still have jobs, I need them to move. Because I got rid of the jobs in a manufacturing plant in Pennsylvania. Now I still have a factory down in Kentucky. If they want to move down, I can still employ them. That's proven not to be as true as it used to be back in the day. It used to be people would follow the jobs. Now people are rooted and tend to stay where they were. People need to be rational. I feel like I shouldn't need to explain that one, but it basically says everybody tries to maximize their own value. If I can have a job here in Cleveland, serving bar for $45,000 a year, or I can have the exact same job at the bar next door for $45,001 per year, I will take that other job every single time because it's an extra dollar. I'm rational. I'll buy something else. Not much, but something. And people need to be willing and able to learn new skills. So if I render something completely obsolete, if I say we don't need any textile workers at all anymore, we don't even need knowledge about textiles, that's completely automated. Well, there's still a lot of people with a lot of knowledge of textiles. So they actually need to be able to go back to school or go to a trade school, go study a trade and learn a new skill. And again, that's been proven not to be true. People like what they've learned. They want to keep using what they've learned. And I get it. It makes sense. So these aren't exclusively true, and it's why we've seen unemployment come when automation is come and displace some of these jobs. So there's also a limit to first order automation, and that is we know more than we can ever tell. This is, I always say this incorrectly, so I've got to look at it. Polanyi's paradox. How do I describe every single thing I do at my job? I can't do it. Sometimes I just do something off instinct. If I see a fly come in, how do I know to swat it away? I can't teach a machine everything that I would love it to do for me. And traditionally, first order automation has been for formal problems that have very clear definitions and very clear solutions. 2 + 2 = 4. No ifs, ands, or buts. We can train the calculator to do that for us. So, unfortunately for the Luddites, value goes up for workers that are good with the new technology, and they weren't necessarily. It could have been a lot of more low-skilled workers that wouldn't have had jobs that now, because they knew the technology, they could replace these high-skilled workers. So on a large scale, there are 2 things that first-order automation really leads to. And the first is polarization of wealth. So here we're looking at 1970 to 2014. So we're looking at a time kind of, before computers to after computers, where a lot of first order automation occurred because of computers. We Excel, talk about how much logical stuff we were able to do just with Excel. And that's one program. Now we've got TurboTax. I don't have to take 6 hours out of my day to do my taxes. There's a lot of first order automation that computers brought. Now there's starting to be a lot of second order automation that computers are starting to bring. But what's really happened is we've seen this dampening effect on the middle class. So if you think of if we kind of envision maybe 1900 and look at just think of the distribution of wealth there, we might have a bell curve. And what we started to see is we kind of push down the middle of the bell curve, and we increase some of the poorest of the poor and increase some of the wealthiest of the wealthy. But people seem to be getting wealthier. Overall, people are getting wealthier, at least in the United States. And the majority of technology has actually aided people. So, yeah, I put 40% of workers out of job, but 60% of them were a lot better off. So if you look at the average, yeah, okay, cool, we're doing better off. So there's pros and cons there. We've also seen a large change in the labor force participation rate. So people are like, oh yeah, unemployment's at an all-time low. Awesome. We also have the labor force participation rate is at an all-time low, and that's people are just staying out of the market, not necessarily looking for jobs. And looking at 1990 to 2000, there was a 7% drop off in the labor force, and this is men aged 25 to 54. So we're not looking at people retiring. We're not looking at people still in school. We're looking at people just quitting and saying, I don't really want a job anymore. This is actually largely due to low-skilled workers finding it harder and harder to find and retain work, and paired with the unwillingness to move. So they just simply withdraw from the market entirely. Paired with that, there is a gender. There's a gender part of this curve where when you look at women, their rate is going up slightly for that amount. So part of it is that women were replacing men in the workforce during that time period. But not 7%. So wealth has gone up for the majority of people, but it's definitely, there are people that were hurt by it as well. So that's kind of the foundation that will lead us into second order automation. So this is where we get into the fun stuff. So if we think back to Polanyi's paradox, we know more than we can ever tell. Machine learning just pushes this aside entirely. Machines, it was said earlier in here that computers learn in a completely different way, but the things that computers can learn, and they can learn to do pretty much anything we ask of them, is what we've been able to prove. So it's no longer, it doesn't matter how much we can tell them, they can learn stuff that we cannot tell them at all anymore. And so now we have computers learning incredibly complex tasks by just studying examples. Exactly like we were talking about with self-driving cars. And this is what is commonly referred to as AI. So I wanted to relate it back to the previous talk and talk about how self-driving cars are going to come into play in the next hopefully a dozen years. So there's literally dozens and dozens of these companies trying to create self-driving cars, and they're getting close. And this is just radically going to change the United States economy, as well as the world economy. So self-driving cars, for all intents and purposes, look like they're going to follow the same pattern as first-order automation. So there's going to be a set of winners. There's going to be a set of losers. The winners are going to be aided by this technology. They're going to be able to do more because of this technology. The losers are going to be put out of work and not able to adapt as quickly. Very non-complete lists. We could make lists that you couldn't even fit on this screen. But winners include anybody involved kind of in data and IT. There's going to be a huge amount of data. We're talking about gigabytes a second of data coming in from these cars. We're going to learn everything about everybody from where they're going to how they're getting there, better traffic routes, where should we put the next roads. There's going to be an incredible amount of data influx. Mechanics, they're going to be winners because they're going to be asked to fix these incredibly complex cars. You can definitely charge more when you have a very complex system like that. Logistics delivery companies, they are going to make a ton of money because they are going to be able to fire all of their drivers. So that brings us to the loser side. Drivers, they are just going to be massively displaced in the workplace. Insurance and injury law, they're going to take massive hits as the safety of these new cars is through the roof. I'm not going to sue anybody now, and everybody's safe. If you even looking at at medical costs of car crashes, we're putting a lot of hospital workers out of work as well. And so a recent study from McKinsey & Co. suggested that self-driving cars are going to transform jobs held by 1 in 9 U.S. workers. And I would say it's going to change all of our lives. So you might say, Ian, what's the problem? There's always winners. There's always losers. This looks like it's going to be the same as first order automation. The most of us are going to be better off. Some of us will be worse off. That's how it goes. So let's look at drivers. So there are over 8.5 million truck drivers in the United States, and there are about 1 million taxi, Uber, and Lyft drivers in the United States. So these new technologies aren't like some of the first order technologies we've seen. They're not like cars where everyone in the United States can learn to drive one. They're not like calculators, which are just taught in school now. Maybe they should be. These are not just simple mechanical devices that say if this then that. These are incredibly complex pieces of technology created by people in this room, and doctors and professionals with decades of knowledge and experience. And to be able to use these technologies, people are going to have to learn a lot about them. And they're going to need maybe a college degree or technical training in a specific field to be able to really excel and switch into a new role. Looking just at the average cost of public schools or public colleges across the United States, and then doing a little bit of back of the napkin math, this could cost anywhere between $400 billion to $1.2 trillion dollars just to educate truck drivers. We're talking just massive amounts of money to re-educate the populations that will be put out of work because of these technologies. So what's going to happen is, not all drivers are going to be able to be trained to be complemented by the new technology. And we're going to see more of the dampening effect of that, middle class, and more of that polarization of really wealthy and really poor. So this isn't unique to self-driving cars at all, but it's really going to be any technology that can replace these higher level human functions. They've got all of the potential to just disrupt the economy. I said years, if not decades away from self-driving cars. Now we're here in 2019, so a little nervous. But you can think about looking at Dr. Watson, for instance. That is gonna revolutionize and enhance how fast we are capable of delivering medical advice. We could see there's estimates that we could see decreases in at least 500,000, by 500,000 of doctors in the United States, and those are kind of on the conservative side. And that's huge. So there's going to be some issues. If we're talking about doctors, some of the most educated people in the United States, they're being displaced, and what are they going to do with all this medical knowledge in their head? So there's going to be some really fascinating issues with second order automation. So this brings us to third order automation. So that's strong AI. So we're either going to have Terminator or Iron Giant. And my answer is, who knows? We have absolutely no insight into this. We've never seen something like this, and we have no idea how it could affect us. So who knows? It's as best your guess is mine. There's 3 typical schools of thought along this, and one is that AI is going to solve all of our problems for us. It's going to create some new problems. Our work's going to be done for us. So what do I do all day? Voltaire says work keeps at rest all evil, and he's got a point. If I'm bored all day, eventually I'm just going to crack. So Mark Zuckerberg is of the school that AI is going to solve everything for us and go AI. AI might kill us all. So I guess that solves all our problems. We don't have to worry about what work we're going to do. Elon Musk is a big proponent of that theory, and he actively works to develop safe artificial intelligence and regulated artificial intelligence, which is interesting just because he owns the company that's, shouldn't get into. And then the third one is kind of where I fall. This is proposed by a mathematician named Kurt Gödel, and he says we're never going to have strong AI. There's just something that humans have that computers can't have. Computers can run these amazing calculations. They can learn things in different ways than humans, but they don't understand. And they can mimic, but they can never fully replace us. I like to believe that just because it's kind of a happy thought. Like, yeah, go humans, we're awesome. But we'll see. So that's the end of it. If there are any questions, I'd love to take some.
Isn't really the end
goal is to really have a humanoid, or more so have some more like a swarm that would be really, really good for manufacturing, like that they act like aliens, or they're not like us that follow a leader, they just react.
So I think the end goal is, well, I think the end goal is different for everybody. I think there are people that really do actively want to create something that mimics a human. I think there are others that really want to create just something that enhances our lives. Again, just going back to, kind of where I stand on strong AI, we won't get there. And what's going to happen, in my personal belief, what will happen is, we're going to have some of the best second order automation where, we're really close to that like human essence, but we're just not quite there. We're going to have amazing chat bots. We're going to have, some of this really cool stuff, but you'll always just slightly know it's not a human. I don't know. Good question. I know I jumped a lot on you without giving any solutions at all, and that was really on purpose because I don't claim to know all the answers. Yeah.
So talking about solutions, like policy decisions or leading economists, do they come up with? I mean, those staggering numbers you have on the slide, but you're probably not supposed to people.
Right. So that's a good segue. So there's a couple really interesting papers, and actually the solutions are really discussed in this book I recommend. It's called The Second Machine Age, Work, Progress, and Prosperity in a Time of Brilliant Technologies. It's by Eric Brynjolfsson and Andrew McAfee. They discuss what they think is going to happen and a lot of proposed solutions and why or not they may or may not work. The one really well thought out solution right now is universal basic income. And the general principle is, you tax the heck out of all of these people that have been winning over and over and over again, and they're up here. And, because we've pushed down this middle and we have two pillars, basically. All we want to do is push the pillars, closer together. So we would give a universal basic income to everybody, actually, but basically up here it'd be so small it doesn't matter, and here it would just help bring that curve up. I don't think it solves the fact of, so what do people do all day? So I don't think it's a complete solution, but it helps with the economics of it, I guess, but not the I'd be bored out of my mind factor.
I've been reading about that because I have a great deal of interest in that particular aspect of it. And one of the things that they found is that the experiments that they're doing, where they're all towns where nobody has to work already. This is already going on. And they find that the populations actually are happier, and that they do not have a problem with people drinking more. In fact, they drink less. Drug abuse is reduced. And generally speaking, the population is like, great, this is fantastic. I don't have to go to work and suffer all day.
We should talk after. I'd love to know what you're reading. That sounds awesome, and it might get me out of this kind of rut I was in after writing this whole presentation.
1-year-old is a 15-year-old too.
No, yeah, this was several years.
Okay.
Yeah.
Universal basic, what other solutions are not bloody and gory are being suggested?
The only other one that I've really seen that I kind of get is just let it happen. It's not an elegant solution, or I guess maybe it is. But the whole thing is that, kind of eventually, if it's helping everybody, eventually it will help people at the bottom more than it will help people at the top. So people at the top will stop doing it. People at the bottom will start, and just eventually kind of, yeah, exactly. And eventually we'll end up with a perfect bell curve again. So that's a theory, but.
Do you think there's a painless way to get there, or a not blood in the streets way of getting to something like the solution like that?
This is opinion, but I personally think that when we see mass displacement on the level of millions and millions and millions of people, there are going to be protests again. We're going to see something similar to a Luddite movement, if I had to guess. Just because if you can imagine telling people, like literally today they have jobs, and if you went to them tomorrow and you told 8 million people they didn't have a job, I wouldn't want to deliver that news, and I don't think most people in that room would take it too well. So yeah.
So a couple things. First, there was an Andrew King how to pronounce it. I heard a segment he did on the NPR show where he kind of addressed like the what do people do all day question, where like hey, more automation that kind of frees up people to, in his words, I think, I'm paraphrasing, to like kind of deal with like actually hard questions, like figuring out what is the meaning of life, why we're here, that kind of stuff.
Definitely.
I don't know. I just kind of thought that was kind of interesting. My second actual question is, are you aware of like any kind of like work or opinion like kind of similar to this book out there that kind of I guess guesses about how strong AI is perceived with respect to quantum computing and the differences that's going to make as far as different things that we're thinking about as far as how computers learn, how they understand, you know.
So from an economic standpoint, you know, economists are anything if they're not slow. They take a while to catch up. Machine learning is actually just now starting to really get into economics, and it's really fascinating. So you know, they haven't touched too much on quantum computing, just given how new it is. Actually, going back to your first question, or your first statement rather, it's a really interesting point you bring up about, you know, people can ponder, you know, the real questions in life. You know, what is life? All you know, get back to philosophy, which is typically thought of as innately human. You know, you can't train a machine to go out and think about the question, what is life? So it's really interesting, and they actually, in this book, they have basically a chapter dedicated to, you know, what would we do all day? And they also talk about people who are most likely to keep their jobs. And it's really interesting that, you know, philosophers, actors, people like cooks, you know, these are things that, I mean, yeah, we could train robots to act, but I don't want to necessarily just go out and watch robot actors if I can go to, you know, right down to Playhouse Square and watch, you know, real life human actors. You know, we could train, you know, like a philosophy chatbot to throw out random questions to us, but you know, we're still the ones thinking about them and stuff like that. You know, it's so some of the more like, you know, painters and stuff like that, we don't necessarily want robot painted art. Maybe a little bit at first because it'd be kind of cool, but those are the jobs that they actually said, you know, those are, if you need to go into a new profession, choose one of those, basically.
There's only 3 types of jobs in the future. One where the human tells the machine what to do. Another one where the machine tells the humans what to do. And the third one, the humans fixing machines.
We can have machines fixing machines. We can make it 2 jobs. Yeah.
To follow up some of the stuff that was in the second machine age, they brought forth, I believe it was either him or Alec Ross in his book, basically said that with something like
Jason, you died.
an example